Okay, in this lesson, this last series of lessons actually, things start to get really cool. We're going to leave the 2D world behind for essentially the first time in your math career. We're going to get a little bit 3D here. So this is sort of a preview of the types of ideas you'll study in Calc 2 and 3 if you go on to continue to take calculus in college. We're going to start with a very simple example though. So let's say I have this horizontal line here. And let's say it goes from x equals 1 to x equals 5. And let's say it is 3 units tall, right? So this is 3 units up the x-axis. We can write that down as f of x equals 3. The question we want to answer, we're going to start with just a very basic question. I shouldn't even say shape. The question is which solid would be produced by rotating this line around the x-axis. So try to imagine that in your head. So we're taking this line and kind of spinning it around. I'll do my best to draw it. So it's always 3 units from the x-axis. We spin it around. It makes these little circular cross sections, right? And because each cross section, each point on the curve is the same distance, all those little circles are the same, right? So wherever we spin it around, you're starting to see the shape maybe? What we get is a solid cylinder, right? So this would all be solid filled in. We get a cylinder with a radius of 3 and a height of 4, okay? So this is called a solid of revolution. So we take a function, we spin it around a certain line. It doesn't have to be the x-axis, but we're going to start with just x-axis for today. And we figure out what shape it makes. And then you may remember, like for a cylinder, the volume of a cylinder is, we'll write it down this way. So pi r squared, so the area of the base, pi r squared times the height. So in this case, we would have a radius of 3, and then my height is 4, right? So here we would have 9 pi times 4, so 36 pi. So we can find the volume of that solid, right? Believe it or not, this formula, what we just did, was an integral problem. So what we are doing when we find the volume of a cylinder is we are cutting that cylinder up into infinitely small circles. So each little slice of pie, so you can picture like, at Thanksgiving when you dump the cranberries out of the can and you get that can-shaped lump of cranberry sauce, you can picture slicing off the top and working your way down, right? That's what we're doing here. We're cutting off little circles and we're finding the area of each circle and we're adding all those areas up to get the volume. That's an integral. That's an integral. Let's write down the integral version of this. So our cylinder goes from 1 to 5. So we represented the height. And then we want to represent this radius. Well, the radius is f of x, right? The radius is just the function, and it's radius squared, so we're going to square it. We're going to multiply it times pi. So this is the area of a circle, right? So pi r squared, and then dx is the height, and then 1 and 5 give us the bounds of the height. So this is also the volume of this cylinder. And let's see what we get here. This is going to be really cool. So we'll do the integral from 1 to 5. Well, f of x is just 3, so 3 pi. Or it's f of x squared, so 3 squared pi dx. That's really the integral of 9 pi dx. And then we get 9 pi x when we integrate, evaluated from 1 to 5. So when we evaluate, 45 pi minus 9 pi, 36 pi. How cool is that? So we just wrote down an integral that represents the volume of this cylinder. And if you're thinking, well, what's the point of that when we already had a formula for that? Our integral is so much more powerful than the volume of a cylinder because I can use this on whatever function that I want. Right? So imagine I had this region R, and this looks like it's a parabola or something like that. Maybe that's f of x equals, I don't know, 0.2x squared. It could be something like that, right? I spin that around, and instead of getting a cylinder now, I get this thing, whatever you want to call it, this round solid. I think you can see the shape of it based on how it looks. I can find the volume of this the same way by chopping it up into little circular cross sections. But I couldn't find that using just like a volume formula that I pulled out of a textbook, right? So that's the power of this. Here is the general formula. We saw this in our example, but I'm going to give it to you. This is what you want to copy down as volume of a solid of revolution. Okay? And I don't want you to memorize this by rote. I want you to think of this as the area of a circle, right? So f of x is the radius. So this is pi r squared. Dx is the height of each little cylinder, right? So dx would be the width of these cross sections. Dx is the change in x, which is the change in height here. Let's do a more challenging example than our little cylinder. Okay, so here we have region R, blah, 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 blah. R is the area between f of x equals x to the third, the x-axis, and the vertical lines x equals 0, x equals 2. Okay, and we're going to spin it around the x-axis. So that would be the integral. We want the volume. It would be the integral from 0 to 2 of x to the third squared times pi dx. And I just follow my model up here. Or you can think of it as pi r squared times the height, because we're making little cylinders. And then I just integrate. So I'm going to pull out my pi because it's going to be a little bit easier from 0 to 2. This becomes x to the 6th dx. And then when I integrate, I get x to the 7th over 7, evaluated from 0 to 2, times pi. And then I just evaluate that on my calculator, right? What you get, this does not want your solutions in terms of pi, it wants a decimal, so what you get is 57.446, right? So I just plugged in 2, plug in 0, I get 0, right? So it's 2 to the 7th over 7 times pi. Okay, that's all there is to it, right? I'm going to show you what this looks like, and this is cool. So what I get is this kind of, it's not a cone because cones have straight line sides, right? This is curvy, but I get this sort of cone shape, right? So this green area is the region that I'm talking about, and then these are my cross sections. That's pretty cool. So what happens now if the region does not revolve around the x-axis? So here we have a similar problem, but instead of revolving this region around the x-axis, we're revolving it around the line y equals 4. Okay, so instead of spinning this around the x-axis, we're making little disks this way around this line that's given to us. That changes our setup a little bit, right? We still want essentially the same thing. So here is what your integral should look like. So it should be the integral from a to b of pi times the radius squared dx. Okay, so it's the same formula. F of x in those other examples was my radius. Now, because f of x is the height of this function, now though we want the distance between 4 and f of x. Okay, I'll show you what that looks like. So I'm going to plug in my bounds. My bounds are going to be 0, and it looks like they intersect at 8. So at the integral from 0 to 8 of pi times 4 minus f of x. 4 minus f of x dx, and that's the radius squared. Okay? So that is still my radius, but because the line that I'm rotating it around has changed, how I write down my radius is changing. Right? So we'll make one substitution here to make it a little bit more clear. So it'd be 4 minus x to the 1/3 plus 2 squared dx. And then I would simplify and integrate that just like I had in the previous problem. Okay. So this formula is really crucial here because this is the general formula for these rotational solids. So no matter what line I'm rotating it around, it's always the formula for the volume of a cylinder, right? So in this case, my radius is here because this represents this distance, my radius.